Now, I would like to discuss some of the questions based on the quick shot. So let me show you my screen first. I believe you have already seen the video of quick shot. So in the quick shot, what we are doing, we are applying to make a sequence in a sorted order. And we have already discussed that the best case scenario is when you are dividing the entire array into two equal halves. And in that case, we get big O of n log n. And the worst scenario is when you are dividing the sequence in such a way that at one side you are getting nothing and other side you are getting n minus 1 element. So if this is the nature of partition, in that case, it gives you big O of n square, which is a worst scenario. Now, one more thing to notice here is this is only fine when you reach to the worst case scenario. Otherwise, it will always be n log n. How? Then we have to see. So if the partitioning is split into some ratio, then we are getting n log n. So if you have this kind of scenario, means if you have size n and if you are dividing in such a way that one side you are getting of array of no size, means there is no array, and the other side you are getting n minus 1. If this is a scenario, then this will give you big O of n square, which is a worst scenario. And when you get the scenario, you get the scenario when your list is already sorted, either in ascending order or in descending order. Now, let us recall what actually means how the this algorithm works. So if you have a series, let's say 2, 9, 16, 32, and let's say 50. This is already sorted in ascending order. And if we apply the quick sort, so in the quick sort, we are doing the partition. So partition, we start with the last element. So we assume one element as a pivot. The last element we assume as a pivot. And in the partition, we are trying to place this element in the correct position. And when you place this element in the correct position, it will divide your array into two parts. One part is less than this element, other part is more than this element. What does it mean? It means, let's say if I am having 2, 9, 3, 7, 5, then when I apply partition, the partition will bring this pivot element in such a way that it will come to the correct position, and the left hand side you will get the element which is less than 5, and right side you will get the element which is more than 5, but these elements are not sorted. So in the partition, we are just dividing into two halves, keeping this element in the correct position, and dividing in such a way that the right side is more than this element, left side is more than this element, and then this is our new problem. We again apply the quick sort in this part and also in this part. This is what we are doing. Now, when we have this kind of scenario, when the elements are already sorted, so what you will observe that this part is already sorted. So when you run the partition, you get 50 here, and you will get here the remaining element, which is of n minus 1, and here we have no element. This is a worst scenario. Means when you apply the partition, one side you get n minus 1 element, other side no element. But this is the only scenario. If your partition divides in any other format or in any other ratio, that is 1 is to 9, 10 is to 200, 3 is to 4, 1 is to 5, whatever the ratio you can think of, in all other cases, it will give you only n log n. So we will see this scenario. Other is we will make one scenario, imaginary scenario, that if the partitioning is happening in such a case that one time it will do worst scenario, other the next time it will do the best scenario. That means when you start with n, the first time it will divide into 0 to n minus 1, then it will divide into n minus 2 by 2, and then it will divide into 0 and n minus 2 by 2 minus 1. Okay, similarly you can do like this. This is another scenario, means at one time it will do worst partitioning, other time it will do best partitioning. So let's see what will happen in this case. So let's say partitioning in some ratio. Let's say 1:9. We are dividing our input in this ratio, and we'll see what is the behavior, what is running time in this case. So let's say we have input n, and we divide into 1:9. So we will get, let's say this is n by 10. This is 9n by 10. We have this kind of a partition. Again, now we have two sub problems. This is the actual problem. We get two sub problems. Now we will apply again quick short in this sub problem, and again the partition is being called, so it will be dividing into n by 100. This is 9n by 100. Every time we are dividing in 1:9 ratio, means the partition is working in such a way that every time it will divide your given array into this partition. So when you move here, it will give you 9n by 100, and this is 81n by 100. So you keep on moving to the next label, and if you move this side, you will get this is 81n by 1000. This is 729n by 1000, and you keep on expanding in this way. And if you remember the quick short, we keep on dividing our array with the help of partition until your array size remains equals to 1. So it keep on dividing until your array consists of only one element. So how to find the cost or the effort of this kind of partition? So when we are doing with this kind of partition, so you can see that initially you apply this much effort, this plus this. So this is something of order n. So you apply this effort, and you are able to get these two sizes. Okay, then again you will do partition. The partition cost is actually theta n. So when you are doing a partition, you are doing the effort of order n, or you can say this is you did this much effort, this much effort. So every time you are doing this much effort. So how to find a total effort? We need to find out how many times we are doing this effort. So we need to find out what is the number of labels we are doing this task. We are doing this partition. So here you can observe that this is going to stop after some iterations or some labels, because here n value is less, but here the n value is more. So it is going to the wider depth. It is going to the more depth. Okay. So how to find out the labels? We need to find out the pattern, that how we are going to form a new size. So if you look at the right hand side, we have n, and then we uh, divided this into n by 10 size, and then we get 81n by 100 size, then we get 72n by 1000 size, and we keep on doing like this until we get array of size 1, or you can say of size n by n. Okay, this is what we need to get to stop. Now we can also represent this as n by 10 by 9 power 0. This is n by 10 power 9 by 1, n by 10 9 by 2, and so on, n by 10 power 9 by k. That means we have reached up to k label. So total label will be 0 to k, means k plus 1 label. We did this effort, and what is the effort we are doing at each label? We are doing big O of n. So this is multiplied by big O of n. This gives you the total cost. So we need to find out what is k here. So k is this value is equivalent to n, then only you can get n by n. So you can say 10 by n power k is equals to n, and when you take the log both sides, you will say this is log n to the base 10 by 9, and this is 1 point something, and we always want to simplify it. Keep in mind, whenever we talk about asymptotic notation, we are not looking for the exact value, but we are looking for the class, and we want to simplify our relation. So we can equate it with the base 2. So we can replace this k with the log 2. So we can say this is log to n number of label plus 1 into big O of n. This will give you n log n. This is your running time whenever you are doing this kind of partition. So to conclude, we can say whenever we are doing a partition in any ratio, it will always give you n log n, except if your ratio is of this nature where you are dividing one side 0 and other side n minus 1. This is one result that we are using in some numericals that I will show you now. Okay, moving to next numerical. That is the next scenario where our partition is working in such a way, so we will get alternate worst and best partition. That means we have n element, we applied partition algorithm, we get into n and n minus 1, and then we apply again partition, we get n minus 2 by 2, n minus 2 by 2, and then you keep on applying in this way. One time best, other time worst. One time best, other time worst. So in order to solve this kind of equation, we need to find the nature of this. Means we need to find a recurrence relation. So here, this is a problem. We are calling it as a Tn, and we did n we apply the partition. That means we applied this much effort, and we get our problem of this much size. So how can we write? I can represent my problem as I did the partition. The cost of partition is theta n, because it will always take this n time. That's why we are saying theta of n. You can even write big O of n, but the notation meaning is because the partition cost is actually n all the time, so we write it as a theta of n plus. When you do this partition work, you are able to reduce the problem into this much size. So you can say you get two problems, Tn minus 2 size plus Tn minus 2 size. So here you can say that this is theta n plus 2Tn minus 2 by 2 size. Now our objective is always to simplify our, write the expression in a simplified form so that we can easily solve it. So here you can see that n by 2 is actually more than n minus 2, more than equals to n minus 2 by 2, because this value is more, this value is less. So if you are replacing any value which is more than this, then it will not affect the big O notation, because in the book in the big O we are looking for the maximum or the worst effort or the maximum effort that is required to solve the problem. So I can even replace this term as a n by 2. So if this is, if I have this format, I can replace Tn minus 2 by Tn by 2, because this is more than this. So that is actually okay, because we are looking for the worst scenario, the maximum effort required. So I can write this as a theta n plus 2Tn by 2. And if you compare this expression with the standard form of Master theorem, you can easily find out a result, and you will say that Tn will be your n log n. So again, here also, if this is a scenario of partition, then also it is n log n. So far we have concluded. So whatever the sequence is given to us, and when we apply the partition, except in one scenario, we are always getting n log n. Let us use this results in some numerical. So I will move to one numerical, and we see that how it can be applied. Here one scenario is given to you, and we need to find out what is the cost of the effort. So the question says, the median of n elements can be found in big O of n time. What is the complexity of the quick shot in which medium is selected as pivot? Now, when we apply the quick shot, we need to start with the pivot. The pivot element is the element that we start with, and in general, we choose the pivot element as the first element or the last element. In our example, in our algorithm, in the video which I have given to you, in that video, I have chosen the pivot element as the last element, but you can also use the pivot element as the first element, and you will get the same kind of result. So what actually we are doing, this is our scenario. We choose this element as a pivot element. We apply the partition, and the partition will keep this element in the correct position, and we will get the two partition of our array. This is what we are getting in the partition, and then you will again call quick sort for this array and quick sort for this array. This is what we are doing. Now the question says, instead of assuming the last element as pivot, you assume the median element as a pivot. So median element is a mid element that actually lies somewhere in the middle of the given sequence. So how to apply this? It says you can find the median element in big O of n time. Now, what is the impact of using the median element as pivot? If you use median element as pivot, that means this element is exactly located at the center. So let's say this is the median element. If you apply the partition, it will exactly divide into two halves. Otherwise, if this is not medium, this is a possibility that when you choose this pivot, which is not a medium, it is possible that this element is maybe placed somewhere here, and you get two partition, which is one partition of this much size, other partition of this much size. But with the partition, but with the median element, the partition is exactly half. Okay, so we'll understand that how the things will work. So the cost of finding the median element. So cost of finding median element is big O of n. This much effort you have to do to find the median element, to find the mid value among the given sequence. So what is required? This is sequence given to you. So instead of starting immediately from the last element, first we find which is the median element. The median element can be placed anywhere. This is sequence, right? So what does it mean? What they are going to say is, let's say, let me frame one example. Let's say 2, 1, 9, 8, 5. This is sequence given to you. So this is actually a middle element is 5, which is not placed in the center, right? Maybe this is a sequence, right? Now, if you look at the sequence, then this is something which comes in between. This has to come in between, right? So we will do some effort to find which is the median element. So we will do an effort to find out that, okay, out of this element, this is median element. So we did big O of n effort. After that, in order to apply the quick sort, that the algorithm which we have discussed, it only works with the first element and the last element. Okay, so you need to bring this element to the last position. So what you will do, you will actually swapping this element, bring 8 here and 5 here. So means the effort required to swap with the last element. So swapping will be just a constant operation. You simply change the two values. Now you will apply the normal method. You will apply the partition method. So the partition cost will be, you can say, big O of n. So after the partition, you will get your array divided into two equal halves. So how you can represent the entire scenario? You will make a recurrence relation. You will say your problem is T of n, where n is the size. You did the effort to find the median element. Then you did effort to swap with the last element. Then you did the partition. And with this much effort, you are able to bring your problem into n by 2, n by 2. Means you get two problem of size n by 2 and n by 2. So you can again represent like this. So now you have two new problems of size n by 2, n by 2. So how you can write this entire thing? You can write as big O of n, and this you can write as 2t n by 2. And if you look at this recurrence relation, which is a very common relation that we have already discussed, this is nothing but this is n log n. So the effort required here is n log n only. Okay, so let's take one more example. Now already solution is given here. This is already there on the e-class. You can check it there. Okay, take one more example here. In quick sort, for sorting the n elements, the n by 4th smallest element is selected as pivot. Again, we are saying that instead of taking the last element as pivot, but we are taking n by 4th smallest element. In the previous case, we have chosen the median element as pivot. But in the given sequence, you are not aware which is the n by 4th smallest. So you need to put some effort to find out which is the n by 4th smallest element. To find this, you have to do this much of effort. So effort required to find n by 4th smallest is big O of n. It is given here. Maybe in the other question this cost is different, but here it is big O of n. So when you get this kind of question, you have to do it accordingly. So to find this smallest element, it is required n big O of n. Again, once you find this element, if you want to apply the quick sort, you need to bring this element to the last position, because our algorithm works on the last position only. So you need to swap the element with the last position, swap with the last element. This requires only constant effort. Only swapping is a big O of 1, and then to apply partition. So partition effort is big O of n. So what is happening when this is your array? When you do the partition, actually you are able to divide your array into this form. One side is n by 4, other side is 3n by 4, something like this. This will happen when you apply the partition, because this pivot element is n by 4 the smallest. So that means when you bring this element to the correct position, then definitely it will make this kind of partition. So how can I represent? I can write that this is my problem. I did some effort, big O of n, to find the n by 4 the smallest element. Then I did effort to swap. Then I did effort to partition, and I am able to make my input size of n by 4 and t 3n by 4. Now we have to simplify it. So this is nothing but big O of n, and this is a ratio. This is, again, we have discussed that any ratio. So we have already discussed the example of 1:9. So this cost you can write directly as n log n, because already we have proved. So what you can say, t of n is nothing but this is consist of big O of n plus big O of n log n, which is nothing but big O of n log n. So again, in our case, in this kind of scenario, the cost is big O of n log n. So here it comes big O of n log n in both the scenarios, but you have to consider the effort whenever it is given in the numerical, and then just apply the values and you will find the answer. So this is the solution here, and it's already there. You can see it later. So T1 and T2 are the time taken to partition the following sequences. So this is sequence given to you. This is already in ascending order. This is descending order. And T1 and T2 are the time for doing the partition. So you need to find out the relationship, means what relationship exists between T1 and T2, means T1 is more than T2, T1 is less than T2, or T1 equals T2. This is you need to identify. So if we look to the quick sort, already we have discussed, whenever your array is sorted, you need to do the maximum effort, because your partition will be of this kind: 0 n minus 1 form or n minus 1 0 form. What does it mean? It means if my array is of this kind, 2 3 21 68, and this is already sorted, if I apply the partition, then what it will happen, I will get, this is my one sub array, other side sub arrays of no size. Reversely, so what I get is I get n minus 1 size, and this is 0 size. Reversely, if my array is of this size, 90, 87, 15, 12. Now what will happen? If I take this as my pivot, then what will happen? Pivot will be kept at the correct position, and you will find here all the element 90, 15, or 87. I don't know what is the sequence. It will depend on the kind of swapping that we are doing. But what is confirmed, that left hand side will be less than 12, right hand side will be more than 12. So there is no element less than 12. We are getting nothing here, but here we are getting 3 elements which are more than this. So we are getting n minus 1 0. So will lead to n square here also, big O of n square here also, big O of n square here also. That means in both the cases, this is the worst scenario and will give you big O of n square. So you can say T1 equals to T2. But what other kind of changes you can expect here? Let's say this is a given sequence, and this is the effort of quick sort in the ascending order, and this is the effort of insertion sort in the descending order. Then you have to compare what is T1 and T2, means what is the relationship. This is descending order insertion sort, ascending order quick sort. You have to find out what is the relationship, or in any other different ways a question can be asked. So what I mean to say is, if you understood the basic, the concept, then question can be asked in many way and you are able to give the answers. So this is some very basic thing that I need to talk to you, so that you can understand the quick shot in a better way, and also you can, I mean, say, explore in a different form. Also, you can understand that what kind of different questions can be asked based on the quick shot.
Yes.
Okay, fine. So bye for now. Take care.